Folks, we're going to talk this time about neutron stars and pulsars. What's a neutron star? When a star has gone supernova, as we've talked about in the past, there is an implosion, great pressures, and there is an explosion outward. Now, the explosions outward produce new nebulae, and the nebula are where new stars are born. And it's that recycling process that gives us continuously new stars in the process of being born. But let's talk about that implosion inward. Now, the pressures are so strong and the forces are so great that when a star goes supernova, what happens is this. It's very unusual. It's really difficult to do. As you may remember from some of your basic chemistry you've had in the past, protons have a mass of 1 and a positive 1 charge. Electrons have a mass of not exactly 0, but really, really small, and a negative 1 charge. Well, in the center of a supernova, what happens is the forces are so great that protons and electrons fuse together and they produce neutrons. The positive and the negative charges cancel, so you end up with a particle of 0 charge, and the mass is just a smidge more than the mass of a proton. So just a tiny bit more. And a lot of people who haven't taken an awful lot of science are not aware of the fact that a neutron is not a fundamental particle. A neutron is actually made up of a proton and an electron that have fused together. So in a supernova, pressures are so large, protons and electrons fuse to produce neutrons. Now, because it is made up of neutrons, there is no electrical charge. It's not a plasma like you're going to have for other stars. And it can be packed very, very densely. So you take something that is the size of our sun, that is just nutty crazy big, and you know that there are millions of Earths that could actually fit inside of the sun. And as a normal star goes through a life cycle, it goes to a white dwarf. Well, if you compare a white dwarf to a neutron stars are very small. So you're talking about something the size of our sun, the mass of our sun, and it is packed very, very tightly, and it can fit into a space maybe 30 to 50 miles across. So about the width of Rhode Island, it can be a very small space, can be a neutron star. So you're talking about something with a lot of density and a very small space. So how much density? Well, you've got the mass of 1.4 to 2 or 3 solar masses times the mass of our sun, and it has been packed into something that is about 50 miles across. What does that mean? That means one teaspoonful of this matter will weigh as much as Mount Everest, which is the tallest mountain, over 1 billion tons. It is almost impossible to imagine something that is that dense. But because it has such a huge density and such a small radius, what you have with a neutron star is you have very, very strong gravity, due to the big mass and the very small radius. Now, neutron stars are also retired stars. They no longer produce any energy via fusion. So how do we know they're there? They're not fusing elements. They're not emitting heat and light like a normal star. So how do we even know that they exist? Well, we know they exist because of some things called pulsars. Back in the 1960s, there was a British scientist named Anthony Hewish, and this is a picture of Anthony Hewish, and he was working with one of his graduate students, a Ms. Jocelyn Bell, and here's a picture of Jocelyn Bell. And what they did is they built a huge antenna array. Now, this might look like a bunch of sticks and wires, and it kind of looks like you're trying to hold up ginseng or grow plants or something on it. But that was a very large antenna that they built. And what they were doing is they were looking for radio signals from outer space. And here's what they found. They actually found signals from space that were not random. We have a lot of radio signals that come from space, and they're just random background noise. There's no regularity to them. There's no consistency to them. Well, but what Bell and Hewish found is they found sounds that, and I'm going to try and reproduce this, they're going to find sounds that sound like tick, 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 very, very regular. So regular that they can be down to the fraction of a second, that these things would be emitting a radio signal like every 1.0673 seconds. I mean, incredibly regular. And they then found another radio source in another part of the sky, and maybe this one was tick, 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 tick. Again, very regular, but maybe at a slightly different rate. They weren't sure what they were finding at first. They actually thought that they might be radio transmissions from space aliens. Maybe this was some sort of alien communication or alien navigation system. So when these were very first discovered, they called them LGM for little green men. Well, eventually they determined that these were not little green men, but these were actually radio sources of neutron stars. I'm going to ask you to listen to some sounds of pulsars when we're done with this video, because it's pretty nifty. When you go to this website, you have to click on the various different pulsars and listen to them, but it's pretty nifty because you're actually hearing radio signals from outer space. So what exactly was giving this tick, 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 these kind of real regular sounds? Each individual pulsar has a very unique frequency. Crab pulsar, which is in the middle of the Crab Nebula, spins around nutty fast, about 30 times per second. The fastest known pulsar actually spins at 640 times per second, or 1/7 the speed of light. What's going on? What's actually producing these radio signals with very regular and very rapid oscillation or changing in pitch? Here's what astronomers have figured out. You start out with a star, and that star, as you know, has some sort of angular momentum. And that angular momentum is when the star has a certain diameter. Well, when a star goes supernova, you have the explosion outward, and you have the implosion inward. And the implosion inward takes something that is 1.5 solar masses, and you now make it so dense that it might have a diameter of maybe 50 miles across. Well, you have then decreased the diameter and made it very, very small. By doing this, this makes the rotational speed very, very fast. So it is going to be very, very fast in its spinning. When you have a neutron star, all of that neutrons conservation of angular momentum basically comes down to something that's going to rotate very fast. So a pulsar is a neutron star that is spinning very quickly. So what's producing the noise? What's producing the pulsar or the pulsing sound? Well, if you recall from what we've done in the past, all objects out in space, not all, but most, and stars certainly definitely do, have a magnetic field around them. Our planet Earth has a magnetic field around it. Our sun has a magnetic field around it. And when something has a magnetic field, if this is the direction in which it is rotating, the end of the magnetic field is typically like this, like the end of a bar magnet, and like this, the other end of the bar magnet, with sort of circular lobes on the left and right side, actually totally encasing the object. If you get this and you start it spinning nutty, nutty, nutty quickly fast, what happens is at the ends where the magnetic fields are more free to move, they're not trapped in these circular shapes, what occurs is there are big areas of radio waves and magnetism that are escaping. And as this swings around, kind of like a lighthouse going around, from our viewpoint here on Earth, if we see this thing, every time that this aims towards us, if this pulsar is spinning around like this, every time that this is spinning towards us, we hear a flash of radio waves. And in the visible spectrum, we can actually sometimes see a visible flash of light, very much like a lighthouse. And so hence this is called the lighthouse model or the lighthouse effect. And that is basically this spinning pulsar, spinning neutron star. We have to be in the right location in order to detect it. If we are watching it from this direction, we'll actually see that spin, we'll see the radio waves. If we are looking at it from this direction, we're not going to necessarily see it or detect that it's even there. So we can't detect every pulsar or spinning neutron star that's out there. It has been hypothesized that in the future, how are we going to navigate in space? And navigating in space is tricky because everything's in motion. Planets, stars, everything's moving. How do you find your point from A to B? Well, pilots today use something which is called VOR navigation. VOR stands for Very High Frequency, Omnidirectional, and Ranging. Basically, you may see one of these. There's one by Old Highway 29 between Eau Claire and Chippewa. This is a VOR station, and this broadcasts radio waves in all directions. Well, the pilot treats that like a signpost in the sky, and this is a small snapshot of an IFR, Instrument Flight Rule map, that pilots use, and this little symbol means a VOR, one of those. And so what a pilot will do is they will fly from one of these to another one, to another one, and instead of just being loose in the sky, which you can be when you can see, if you can't see because the weather's bad, they fly from one of these to the next. It's been hypothesized in the future that what we're going to do is we're going to use pulsars for this, that they can have a pulsar from this star and then a pulsar from that star and a pulsar from maybe over here, and use that triangulation method to try and figure out where the heck they are, how fast they're going, and how to get from point A to point B on long interstellar missions. Here's another video on pulsars I'm going to ask you to watch, and it's pretty good. I think you'll enjoy it. But we're going to finish this out because we only have 1 or 2 slides to go. And the last kind of new idea is the concept of something which is called a magnetar. Now, a magnetar is, again, a special kind of neutron star, but it's a type of neutron star with an incredibly nutty strong magnetic field. It will pulse every 1 to 10 seconds, but instead of pulsing in the radio frequency range, every 1 to 10 seconds, it is going to emit a huge burst of X-rays or gamma rays. And these X-rays or gamma rays, if you remember, these are stronger, more high energy types of wavelengths than radio waves. Again, this has to do with the magnetic field of these objects, and when these magnetic pulses let loose, they are very, 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 very strong. If there was a magnetar near planet Earth, it could, depending upon how new, it could actually suck the iron right out of your blood. Huge, massive magnetic fields. They're weird, crazy things that scientists have found out in space. So it is the most magnetic thing that we know of. Again, I'm going to ask you to watch a little video of this, and that will do for the moment. So here's where we are so far. We talked about normal stars, nebula, average, expand to a red giant. As they burn off and change fuel, planetary nebula, white dwarf, black dwarf, and then done. Big stars burn fast, go blue because that's a hot color. Then they go red supergiant, supernova when this red supergiant collapses down, and then they can go into neutron stars, pulsars, magnetars. But then there's this little guy, black holes. The next chapter we're going to spend all about black holes, because black holes are part of probably the weirdest thing out there, and there's always a lot of cool stuff to discuss about them. So that will do for the moment, and we'll see you next time.